Yeah, we go to the last presentation in this section by Stanislav Lenart of the Zag. I don't know the abbreviation, but Zag Institute, University of Maribor. This will be on the resilience of stabilized and conventional high-speed railway track subway. Stanislav, go ahead, please.
Can you hear me?
Yeah, and see the presentation.
You see my presentation. Okay, yeah. Great.
It's okay.
Yeah, so I'm going to present a project which was performed by large-scale triaxial apparatus at Slovenian National Building and Civil Engineering Institute. We collaborate with University of Maribor in GeoLab project. This apparatus is actually the smallest piece of equipment participating in GeoLab project, and it's used for technology readiness, the lowest technology readiness levels. It can be used for mechanical testing of various geomaterials. What is it? Its advantage is that it's actually large-scale triaxial apparatus, which can be used in different modes, in triaxial, direct shear, simple shear, and also different kind of custom-made loadings of specimens, also with principal stress rotations. As Ton mentioned earlier, we use it also for small-scale traffic load simulators. The specimen which can be tested is of size up to 80 centimeters in height, 40 to 40 centimeters in square. Here are 3 photos presenting different modes of testing. In this particular project, which I will present, University Hsrtsub from Turkey proposed testing of railway subgrade to see what are its deformation characteristics. Basically, very simple test. So to what we normally do in small scales, but the advantage and why this apparatus was used is that with this scale, with this size of specimen, we can actually test coarse material like ballast, and that was also tested in this test. So the objective was to do characterization of ballast track, particularly ballast material. What is the effect when it becomes fold? So we tested clean folded and folded ballast behavior, and the final goal is to optimize the rehabilitation work of on old railway tracks. All ballast railway tracks, ballast become dirty with time, and sometimes the railway managers do not really know what is the final level of dirtiness of ballast when it's necessary to clean it or particularly to replace it. So the work plan has been to perform simple shear test on this particular material with cyclic loading. Confining pressure was corresponded to K0 condition, and the vertical load which was used was correspond to the 22.5 kilonewtons per axle load, which is standardized in for railways for this kind of track, which was analyzed. So two real materials from ballast materials from site were used during the reconstruction of one railway track. We got this material. So on the right side you can see clean ballast, and this clean ballast was installed instead of dirty ballast on the left side, which was excavated from the railway track. For installation of specimens, we used more or less similar relative density of both two materials. Also, it's clear that densities for these two materials are not the same, particularly if we would use optimum density or something what we can achieve with high compacted approach. So that's the apparatus. It's as I said, simple shear mode has been used. Displacement are measured on site and on one front side of the specimen. As all those LVDTs are installed directly on frames, it's possible to measure very accurately deformation. And the loading procedure which we used is described here in this table. You can see we try to start with very small strain cycles to see what is the response. That's how the displacement increased. And we decided to change the loading rate during the cycling. So with an idea to have the same, approximately the same time for every load cycle. So when we used very small strain, the loading rate was small, while for large displacement, loading rate was increased. On the left side, you can see how the specimen deformed in later cycles. While here we have hysteresis curves for two typical tests. Obviously, yeah, on the lower pictures, we have loading cycles at very small strain rate range, while at the top there is a total loading history for both two samples. So with this project, we characterize deformation properties of two types of ballast. The project was comparing to previous presented project was quite simple and short. In 2 weeks, everything was performed. We observed noticeably lower stiffness of fold ballast compared to the clean ballast, what was also expected. So in this experiment finished just recently, and so further step is to evaluate all those deformation properties and use them in numerical analysis. And the final goal is to evaluate what can be expected deformation properties of such ballast track when ballast is folded. So thank you very much for this opportunity, and Tom, you can go on.
Okay.